Now, let us look at response to suddenly applied inputs. So, we have an input x of n, it has z transform x of z, it is applied to an LTI system with transfer function h of z, and this h of z belongs to the rational class of transfer functions. Therefore, it can be represented as b of z over a of z, and hence y of n in the time domain is the convolution of the input and the impulse response. In the transform domain, y of z is x of z times b of z over a of z. We will further assume that x of z is also a rational z transform. Therefore, x of z is of the form p of z over q of z, and hence y of z is the product of these two. So, this is p of z by q of z times b of z over a of z. Now, to make the discussion simple, what we will do is we will assume all the poles are simple. All poles are simple. Therefore, we are interested in finding the time domain response, and because this belongs to the rational class, the natural thing to do would be to do partial fraction expansion. Therefore, this is p of z times b of z, and the first thing you need to do for partial fraction expansion is factor the denominator polynomial. So, this is 1 k going from 1 to n suffix x. So, these are the number of poles contributed by q of z. So, this is 1 minus psi k z inverse. So, this is the polynomial q of z factored into its roots, and we have the other part. So, this is k going from 1 to n suffix h times 1 minus p k z inverse. And now, we will find the residues for each of these factors. So, now let me again write the the partial fraction expansion in this form. So, this goes from k 1 to n x a k by 1 minus psi k z inverse plus k going from 1 to n h b k by 1 minus p k z inverse, and we will assume causality. And hence, the time domain response becomes like this. So, this is k going from 1 to n suffix x a k psi k power n u of n. So, this is the inverse transform of 1 by 1 minus psi k z inverse plus k going from 1 to n suffix h b k p k power n u of n. These are the two terms or two sets of terms that are present in the output. Now, if you notice, these are coming from the input. These terms are contributed by the Z transform of the input. Therefore, these are called as the input modes. These set of exponentials are contributed by the system. So, these are called the system modes, and they are also known as natural modes. Now, if the system is stable, clearly we have assumed causality because of the form of the inverse Z transform that we have written, then all poles will lie strictly inside the unit circle. Therefore, the natural modes will eventually die out. Natural modes will eventually die out because the system is stable. Of course, if all the psi k are also magnitude strictly less than 1, they also eventually will die out. But we can be guaranteed that the system mode or the natural mode, they all will die out because the system is causal and stable. So, what this tells you is, if you have a system and to that you apply an input, the output will contain two parts. One part will be the natural modes of the system, which eventually will die out for causal and stable systems, and the other part corresponds to the input modes. So, suddenly excited system will always contain two parts. One part will correspond to the input modes, the other part will correspond to the natural modes of the system. Now, let us take a simple example to illustrate this. So, we have 1 by 1 minus Az inverse as the transfer function of the system, and then to this we apply b to the n u of n. So, now let us look at what the output is. Y of z is x of z times h of z, x of z is 1 by 1 minus bz inverse times h of z is 1 by 1 minus az inverse, and when you do partial fraction expansion, you get 1 by b minus a, b by 1 minus bz inverse minus a by 1 minus az inverse. Very easy to see that when you simplify this, you get back y of z. And if you, by the way, before we get into the expression of y of n, what is it that we have assumed here? Has any assumption been made? Yeah, very good. B is not equal to A. Therefore, this is b times this, after all, is b to the n u of n by b minus a minus a by b minus a times a to the n u of n, and this is easily seen to be b to the n plus 1 u of n minus a to the n plus 1 u of n. So, this is the output, and now you are able to recognize the input mode and the natural mode. So, this is the input mode and this is the system mode or the natural mode. Therefore, when the system whose transfer function is 1 by 1 minus a z inverse is suddenly excited by b to the n u of n, the output also will contain a component that corresponds to b to the n u of n. It will have a scale factor. In this case, the scale factor happens to be b by b minus a, but you will also have the system mode, and that is given by a by b minus a times a to the n u of n. And this is the system mode which eventually will die out because we have assumed the system to be causal and stable. And if to this particular system, instead of b to the n u of n, if you had applied say cosine omega naught n u of n, you can go through the exercise similar to what you have done here. Again, you will be able to write the transform of y of n in the form x of z times h of z, and if you did partial fraction expansion, when the input now is cosine omega naught n u of n, you will again have two parts. One part will involve 1 by 1 minus a z inverse, which in turn will give rise to a component of the form a to the n u of n. The other part will have a form that is cosine omega naught n, but what will be different is it will have an amplitude that is different from unity. If the input amplitude is 1, output amplitude will be whatever the residue is, and there will also be a phase shift, and there will also be this transient response. Therefore, when you apply cosine omega naught n to this system, output will have a component that corresponds to cosine omega naught n. In addition, there will be a term that is similar to this, and this is the transient response. All right. So, you can break the output as steady state response and transient response, and to get a better understanding that comes from this kind of classifying the partial fraction expansion of y of z. Suppose to the same system, you now apply E of n u of n, a to the n u of n, and you can easily see that y of z is 1 by 1 minus a z inverse whole squared. and this in turn will give rise to an output of the form n plus 1 times a to the n u of n, which is just the inverse z transform of 1 by 1 minus a z inverse whole squared. Now, if you look at this, apart from recognizing the algebraic expression for what it is, does anything else strike you? Okay, magnitude. Okay, all right, that's a good observation. All right. Okay, I'll come to that point in a minute. I mean, you're all saying some aspects of the phenomenon that this represents. So, the input mode is a power n u of n. The system mode also is a power n u of n. What will happen when you excite a system at its natural modes? I thought I heard someone say the right answer. So, this is indeed resonance. So, that is why the response initially grows, but then eventually exponential decay is stronger than polynomial growth, therefore, the response dies down. So, this is indeed exactly the phenomenon of resonance, which is what you expect whenever you excite a system at its natural modes. And this is a good place to point out some of the things that you had encountered before in signals and systems. I am assuming you must have been told about zero input response and zero state response, right. So, let us revisit that in this context. Even in the Laplace case, exactly the same arguments hold. So, if those arguments have been pointed out, what we are going to point out now is just exactly the same kind of arguments that were made then. So, zero input response. So, this is typically abbreviated as ZIR. So, what is happening here is the input is 0 and system may or may not have initial conditions. If the system has some initial conditions present, then the zero input response, what do you expect in the output? What modes do you expect in the output? The output will contain only natural modes. So, therefore, output will contain only natural modes. So, the continuous time case analogy is, if you had an RLC network and if there were initial capacitor voltages and inductor currents, and if the input is made 0, all these things will decay and the output will contain only the system modes. Now, let us consider the zero state response. So, this is abbreviated as ZSR. So, all the initial conditions have been zeroed out and then you are applying an input and output will contain what? Both input modes as well as natural modes. So, will contain both input modes and natural modes. Now, when you are trying to solve differential equations in continuous time case, the standard approach is to consider the homogeneous equation, get a solution, and then you will evaluate the complementary function. So, same approach also holds for linear constant coefficient difference equations. You solve for the homogeneous equation and get one solution, and then you will solve for the particular solution. So, LCCDE, whether D stands for differential or difference, the general approach is same. Homogeneous equation will give rise to one solution, and then the particular integral in the differential equation case and particular solution in the difference equation case. And the homogeneous equation, what kind of modes do you expect? This will contain only the natural modes, because what you are going to do there is you are going to set all the input to 0 and you will solve the homogeneous equation. Homogeneous equation will not contain any input terms, and for an nth order equation there will be in general n unknown constants, and to pin these constants down you need auxiliary conditions, which are called as initial conditions if they are specified at the origin. And once you have this, then you can get the final solution as far as the homogeneous equation is concerned. In the particular solution, particular integral, there are no unknown constants in the solution, and you are told that the form of the particular solution has the same form as the input. Therefore, in terms of modes, what do you expect? Which modes will be present in the particular solution? Only the input modes will be present. And together they form the complete solution. Now, this is the mathematician's way of solving this. This is the electrical engineering way of solving the problem. And if you look at this, in the 0 state response, you will find input modes as well as natural modes. The part that contains the input mode will exactly be the particular solution, and the natural modes which occur both in the 0 state response as well as the 0 input response, if you add them up together they will give rise to the natural modes present in the homogeneous solution. That is all. So, the natural modes, the way we look at the output given the system viewpoint, they get split into 0 input response as well as 0 state response, and the 0 state response, the output containing the input modes will correspond to the particular solution. Now, let us quickly look at some typical time domain response. Yes, is there a question? Yeah, and if a mode exists both in 0 input as well as 0 state, it necessarily has to be natural modes. Only these are the modes that are common to both 0 input and 0 state. Because they arise the way the system is interconnected. which will manifest itself when you zero out the input and let the initial conditions decay out, or when you supply a sudden input to a system, the natural modes will manifest themselves. So, only natural modes are common between these two. Does that answer the question? Okay. So, now let us look at typical time domain response to typical pole locations. So, this is just a recap in pictorial form of what you have already learned. I think this is from Transforms and Applications Handbook by Polarica. So, this is a simple pole here. So, M represents the order. So, if your pole is here on the real axis, it will have the form a to the n u of n, and because a is less than 1, it is actually between 0 and 1, it decays down as shown here, exponential decay. As the pole moves closer to the unit circle, the decay rate will become less and less, and when the pole is on the unit circle, there is no decay at all. So, this is 1 by 1 minus z inverse in terms of transfer function. So, this is u of n, and now if the pole moves outside the unit circle, it is still of the form a to the n u of n, only that it is a growing exponential because a is greater than 1. Say for example, if a were 2, this will be 2 to the n u of n, whereas this could be half to the n u of n. And if the pole were here, so the pole is between 0 and minus 1. So, this could correspond to an example like minus half whole to the n. So, minus half whole to the n is minus 1 to the n times half to the n. So, you have the exponential decay, but terms alternate in sign. And if the pole is here, it is at z equal to minus 1. So, this is minus 1 to the n u of n. So, 1 by 1 plus z inverse, this is the inverse z transform. And continuing the same thing, if now the pole were outside the unit circle, but on this side of the axis, you will have a growing exponential envelope, but in addition to that, you also have the sign alternating between terms. So, this is as far as simple real pole, and now we look at double poles. So, instead of first order pole, if you had a second order pole, the output time domain expression has the form n times a to the n. The exact expression is n plus 1 times a to the n u of n. N a to the n u of n, initially there will be growth, because for small values the polynomial growth will win over exponential decay, but eventually exponential decay will be the dominating factor. Now, if you had a double pole, the output will have the form n times u of n or n plus 1 times u of n. So, which is what is shown here. Actually, this corresponds to n u of n, because at n equal to 0 you have output to be 0. So, it is a ramp. If it were outside, it will be n times a to the n u of n, but now magnitude of a is greater than 1, therefore, you have this growth. And exactly the same kind of thing when the pole is on the negative real axis. So, the envelope is still of the form n times a to the n, but you have terms alternating in sign. If you have a double order pole at z equal to minus 1, it is a ramp, but with alternating sign, and this is for on the real axis outside the unit circle. The main point is the envelope is similar, but signs alternate. Now, the complex conjugate case. So, if you had two complex conjugate poles, radius r, angle omega naught and minus omega naught, then this is how the form r to the n cosine omega naught n plus theta. So, the envelope will decay as r to the n, and the alternation inside is governed by omega naught. and if r were 1, you will get a pure sinusoid because there is no exponential decay. If r were greater than 1, the exponential growth is signified by r to the n, where r is greater than 1. And if you had second order roots on the unit circle, the envelope is still linear ramp, but you also have oscillations. So, these kind of give you some feel for time domain behavior versus z plane pole locations. So, there is nothing new, it is just a pictorial representation of all the formulas that we had seen earlier.